We're talking today about why do we use Clojure and why do we think we go faster with it. It's mostly going to be a software engineering heavy kind of talk. There'll be a few parts where it gets slightly technical, but don't worry about that much if you don't understand certain things. It's for the engineering purpose that we're bringing them up. So the main thing we're here to talk about is making these very tiny little fine-grained abstractions as libraries and building up your code that way is really what allows us to go very fast. And at the beginning, you pay some dues because you build some things where, some people might say, why would you ever write that in-house? Just use X instead. But then shortly afterward, as you start to tackle more and more complicated problems, these little small abstractions that you built up come in handy in a way that it wouldn't from a framework. And you can see over time these things evolving, like Hadoop, for example. That whole ecosystem was originally this really, as I understand it, terrible and gnarly code base that Doug Cutting put together, which then was kind of factored out over time into several different projects. And now they've pulled out Zookeeper, and et cetera. So even with these things that start out very monolithic, I think they head in this direction over time. And it's toward their detriment when they don't. Clojure is particularly well suited to this. I think functional programming in general is, but Clojure in particular is very good for some specific reasons that we're going to go into later in terms of the syntax, simplicity, et cetera. And for that reason, we love Clojure. We use it almost exclusively. We have almost no other code in any language other than Clojure, with the exception of JavaScript, obviously, and Objective-C for the iPhone apps. So about us, what is Prismatic? What does this thing do? So as Alex was saying, this thing is a content discovery engine, essentially. It's sort of like a post-search, machine learning-oriented kind of product. It is a consumer product, and it's meant to be basically the newspaper of the world. So it's meant to grow to be very, very large scale. And what it does is quite complicated. So we've thought from the beginning about how to cut corners and also how to make sure we don't paint ourselves into a corner, which would be very easy to do with a system like this, so that it wouldn't scale past, say, like 100,000 users. We personalize feeds based on your interests. So we learn about your interests, by the way, I forgot to mention this, from Twitter, Facebook, et cetera. You sign up, we learn about you, we give you feeds based on your interests. It's a pretty simple proposition. And then we let you explore out to new interests, which is also really important. That means we have to tackle search. That means we have to know similarities between topics and so on, and let you navigate along those edges. So we'll get into that all with a live demo at the end. But here's like a quick snapshot of what the product looks like so you can get an idea. It's very minimal. It's well designed. We also focus a lot on design. You can see you just basically have a core newsfeed here. There's nothing revolutionary there. It's just showing you articles. You can notice a couple of interesting things, though. So notice on that second article, you have the 10 related stories. So that's clustering, which we'll get into in a little bit. And that's very, very hard to do in the way that we do it. And also you can see that all the articles on the lower left corner there in the header have been labeled with their topics. And those are basically correct for the most part. You can even see here on the bottom we have bowling and interior design. You're not going to find a lot of systems in the world that are going to show you articles and the connection of those. But Prismatic will, right? That's what it's all about right there. So who builds this thing? It's me. It's just only me, really. No, I'm just kidding. It's not. I actually don't do anything. These three are the smart ones. And this is it. This is our whole Clojure team. We have, obviously, front-end product-facing work. We have designers and so on. But the whole back end is all built by these four people, and mostly these three. I actually don't do any work anymore. I'm more important now. So, no, I'm just kidding. I don't. Actually, what you don't know is that I don't do any of the fun stuff anymore. These guys get to do all the fun stuff, and all I do is like invite campaign code and stuff like that, right? So, because I can't focus long enough to tackle the hard things, so I only get to do like trivial bug fixes and stuff like that now. It's awesome. And we don't have any of these guys either. Yeah. So there's none of those guys in the mix intentionally. It's tough, but yeah, we screen for that during the hiring process. So what do we build? We build these crawlers, which are somewhat like traditional web crawlers, but they're a bit different because they mostly only crawl social networks. And also because all the activity that we're going after is changing all the time, it's a mix of crawling and polling, right? You're constantly finding new things, and you're constantly polling them to see what's getting updated. And we poll smartly based on how often things change. So the crawlers, in a sense, are actually a far more efficient way of getting all of Twitter. So we have most of Twitter in memory on servers. But we don't need to take the firehose. And that the firehose thing has lots and lots of additional spammy data, right? Most of the data is just rubbish. And you'd rather not deal with processing that and learning how to drop it on the floor if you don't have to. Better to not even have it come in at all. And so if you're smartly crawling around, we've found ways to basically avoid having a lot of the rubbish come in the first place. Social graph analysis. This is just understanding who you are and how you're connected to your friends and how that relates to your interests, because we use all that for ranking. We also use it for bootstrapping. If any of you have signed up, when you have the initial onboarding suggestions, these are largely based on both your social graph and all the stuff that you share. Topic modeling. This is, you've seen, right, we apply labels to documents as we showed in the first part there. And then relevance ranking. So all this information at the end of the day is taken together to re-rank news feeds for you. On each request in real time, news feeds are re-ranked. So we'll get into that in a bit, but that's pretty tough to do. Okay. So news feeds. So the first thing that we have to do to build news feeds is, as documents come in, we need to know, have we seen this before or not? And if we haven't, then we need to do lots of work on it. We need to go and extract all the entities. We need to do all the tokenization and everything like that. We need to apply topic labels. We need to cluster them and see if it's a member of a cluster, if it starts a new one, et cetera. So there's all these kinds of things happening in this real-time indexing pipeline. I mentioned the clustering already. We mentioned the real-time personal re-ranking. The personal re-ranking is interesting. What happens really is that every time you make a request, we have all the information about you in memory on a machine, which also has all the documents that you could potentially see for that feed. So if you make a request, say, for a topic feed, because we have feeds by topic, or for your home feed, we take all this information into account. We also take into account your interests that you explicitly add in the app. And all these things are used to personally re-rank. It's really quite an interesting problem because there's social signals, there's information about your interests. One of the things that we found that's really neat about interests is that when you get a home news feed, in order for this to really be a new experience and not just like, a rejiggered version of your Twitter feed or whatever, which is what's been done a lot, but not really where we're trying to go. One of the biggest problems is to diversify over your interests, right? I think a lot of us here in this room probably follow lots of tech stuff, whether it be technical or about startups or tech as a business in general. And so we see lots and lots of this kind of stuff. And if I give you just a better version of that, well, that's not really very cool, to be honest, right? There's so many other things out there for that. And one thing that could be cool is if you're getting like a Clojure feed and a Haskell feed and a functional programming feed and stuff like that, and you're not able to get this somewhere else. That's pretty cool. But what's even cooler is being able to diversify over all your different interests and make sure that you're getting a good mix of other stuff into there, right? And so decaying weights as you include stories in a feed such that you can see things across all your interests is a really important problem. So the real-time personalized re-ranking is actually a really, really big deal. It's very difficult to get right, and it's an example of a problem that our team is really well suited to deal with, because all of us running product and running research are kind of the self-same people, right? So we get to think about the kind of vibe that we're trying to create and so on, and that comes back around and influences the research. So that's really cool. And of course, all this has to happen very fast, right? All that re-ranking is happening in under 200 milliseconds. So obviously it's all in memory and it's all very, very customized. So we tend to roll our own, and I know what you're thinking. That's tobacco there in the photo. So Yes, libraries are greater than frameworks. I think everybody mostly agrees with this at this point. I don't think this is a very controversial point. Don't take your precious functions and give them off to some weird thing to run that you don't understand. It's a terrible idea. And we are almost entirely Clojure. We really don't use hardly any Java at all. And this is really important to stress because at the beginning this wasn't the case, but we found over time that you really don't need much. With some clever use of macros and some of the recent changes to Clojure over the past year, you really don't need to do hardly any Java at all. So let me take a break for a second. The first thing we're going to talk about is flop, and this is really hardcore, fast math, right? So this is the error you would think, like, yeah, just you have to drop out of Clojure here, but we don't at all. This stuff's 100% Clojure with tiny bit of Java for one particular thing that actually might be able to go away. We haven't revisited it for a while, but it actually might be able to go away. So oftentimes when you're doing fast math for machine learning and so on, you're obviously doing things with mutation. It's a necessary evil, but it can be a pain in the ass sometimes in Clojure. And here's an example of something really simple. And the big thing that I don't like here is really the indexing in, right? Like manually indexing into collections when you're processing two of them in parallel like this is really kind of tedious and error-prone thing that I'd rather not do, to be honest about it. So, and I should mention the specifics here. So we're just adding 5 plus j to the jth element of the array here. So now we're going to look at it in flop. So even when you're type hinting, we've also found you can get inefficient code. There's nothing that guarantees that something's going to blow up. If you want it to run fast, there's nothing currently in Clojure that can guarantee this will run fast, and it will like barf on you if you're causing reflection. But we actually want to do that for some of our core code. We actually want it to blow up if it's going to yield code that reflects, right? We don't want to run that code. So one of the things we've done in flop is exactly that. So all these core macros like the afill you see here, these things will puke if there's reflection inside of them. So you can't even run the code if it reflects. So here you see we weasel out of the indexing, right? That's kind of all you want to get to. You just want to get rid of all the syntax that you can and get it behind some place where you can smartly check for certain things. And it can't, for example, reflection, right? That's really the big thing that you want to avoid. This is one of the rare uses of macros that we have. I mean, we don't use macros much. In general, they're mostly bad, except for when you need them, right? All the typical stuff. And here's our do array. This is the guy who's used all over the place. You can just see he's doing these bindings, and here we're just printing them out. We can even bind out the index if we need to use that to access data in some way in the computation. And that's it. It's really it's just like a do-seek thing, except you don't really want to be Cartesian here. You just want to go over the two sequences in parallel, right? Which happens all the time. This is what you always do. And here's a canonical example is dot product. We're going to get into a little bit of math here for a couple slides, but it's going to be pretty light. And if you get lost at any point, don't worry about it. This part here is really simple. So dot product is just the pairwise product of two vectors, like math vectors, not Clojure vectors. Here we go. So use it all the time in machine learning for prediction. With prediction, all we're trying to do is maximize the dot product. We're trying to basically select the feature which maximizes the dot product with some weight vector, right? That's really all we're trying to do. And we also do it all the time in training where oftentimes probabilities are estimated with exponentiated dot products. So that basically means you're doing even more dot products, right? So dot products, you do them all the time. The whole point of this is dot products happen all the time. It's in the inner loop, and it has to be very fast. So that's it. That's the whole point. And here we see dot product in native Clojure. Again, it's not that big of a deal, but the A-gets I'd rather not have. And the A-reduce is a bit funky, right? I don't know if any of you have used A-reduce, but it's a bit funky. It's one of these functions that you're never quite sure what the arg order is. You know, you go to throw down an A-reduce, and you're like, I don't know I'm not sure what order these things go in, right? And you have to look it up in the docs, and it's not cool. And then here it is in native Java. Again, I mean, here the situation's no better, right? And I've been writing this kind of code for a very long time, and I really hate the indexing part, right? It's a pain in the ass. It's error prone, and we're using really simple examples here to illustrate a point. And obviously, if you're just, this is trivial, right? You're just multiplying together two numbers and you have two indexes there. But if you have something really complicated, this starts to become non-trivial, and it's really easy to screw something up. And so that's the point here. It's not just about speed, it's also about correctness. So in flop, this is all we have, right? It looks like the math. That's about as close to the math as you're going to get. You're summing over all the w's from wx and x from x of s, and you're taking the product. That's it. All right. A little bit more complicated example is expected log probabilities. So here, what we're doing is we're taking these psi-i's. Each of these psi-i's is the expectation of the log of the theta I given the alpha, right? So, and don't worry about if you don't understand what any of this means or this fancy Dirichlet thing. Don't worry about that. The important part here is below is this funky function there, this digamma. So for each of the psi-i's, we're basically doing digamma of alpha I minus digamma of the sum of all the alpha i's, right? So might look a little funky. Don't worry about that. The important part is this digamma function here. This guy is really expensive to compute. So now we're in the very similar situation as the dot product, right? It's a pretty trivial looking top level calculation. But the problem is that digamma guy is pretty gnarly. That's not multiplication. And so you can write this kind of thing in flop again, but it's going to be very fast. And this is very important because this guy is the inner loop of topic modeling. So this you're going to be doing as much as you're doing dot products, but the problem is the digamma function is very expensive to compute. And it's only an estimation as it is, right? So these things are always pretty burly. That right there is basically the core of what a lot of our code looks like that underlies a lot of our machine learning libraries. It's very simple series of functions like this that are written in terms of flop abstractions, and then we're encapsulating the details of some more difficult function behind a simple call like so. So this flop library achieves the same perf as Java, more or less. It's pretty fast. It's so fast that we have no problems with any of this stuff anymore. And best of all, you can write a lot of really complicated code in a very small number of lines. So optimization under 180 lines, LDI-style topic modeling under 180 lines. If you've seen this kind of code before, you know that this stuff is hard. Like doing this in 180 lines is pretty spectacular. It's great for a number of reasons besides the fact that it's fast, right? It's much easier to verify that things are correct this way. Also, this kind of code is very hard to test, right? So you can't just say, like, unit test this stuff and it's going to be fine. This kind of stuff is very, very, very difficult to test. And a lot of times it's probabilistic, so it's not even clear that you can necessarily write a test that's deterministic. And you don't necessarily want to try to, like, mock out all kinds of certain things in order to try to make it deterministic. That's not always a good idea. So it is very, very valuable to distill the code down to the point where you can kind of read it and verify that it's correct on one screen at a time. So that's flop in a nutshell. So now we'll go into some of our plumbing, some storage and compute abstractions that we have. So store is the first one. Store is pretty cool. Actually, we use it all the time. And it's basically just it's an abstraction over key value store that is backed by memory, file system, S3, BDB, Mongo, SQL. We had React behind there before. We got everything that you can possibly imagine behind this interface. And we use the specific features of the underlying store, obviously, right? We do things very efficiently. If there's a smarter way to update or custom ways to flush or whatever, we do this on a store-by-store basis. And this is very, very, very useful. Like, we did this because of previous experience so everybody knows the get and put. That's easy to do. We call a bucket like a key value store. That's our kind of primitive key value store. But the big deal is the updates, right? People have worked with this stuff a lot, know that the thing that's difficult is really the read, modify, write kind of pattern that comes up all the time. And so the get and the put are not such a big deal. But the update is. And so we have this merge bucket, right, which is another one of the protocols that that buckets can reify. And merge basically takes care of this for you. So at the time when you construct your bucket, you inject it with a merge function, and that merge function allows you to merge data. So you can just, in the same way that you could do get or put, you can do merge. And merge is going to be smart about where the data is, how to merge it in, et cetera. Because the thing that happens for us, obviously, is we have a huge amounts of streaming data that are always coming in, which we're aggregating. And so you don't want to be read, modifying, and writing, even if the store that you're supposedly dealing with under the hood is supposed to be efficient about this kind of thing, because it doesn't know the structure of your data like you do. So if you have a key value situation and you have some funky map or other data structure that you're merging, you'd rather do that in memory. You'd rather keep that in an in-memory, like, mutable hash map, and then flush it periodically, rather than going back and forth and round-tripping to the data store and relying on it to do that for you. Also, I forgot to mention there's sync, and we'll come back to this in a couple slides. Sync is a big deal, too. That has to deal with all of the buffering and flushing, as well as all of the caching and checkpointing kind of operations that come up. So let's see. Also, the other thing that I should mention here is it's really useful to get this stuff behind a protocol, because then you can abstract the network away. And oftentimes with key value stores, or any kind of store for that matter, whether it's Document or these other various hybrid stores that are coming up, it doesn't have built-in network facilities, and if it does, they're not always consistent. And the reason we put all of our data stores behind an API is that we can then implement those APIs for the network rather than for each individual store. So anytime you hook up a new store and implement the protocol, you get everything for free, right? Which is really nice. And it also means that we can deal with like all the robustness and error handling things and all that in one place instead of dealing with it on a per store basis. It also means that you can easily swap these things. The in-memory one is great, obviously, for this reason, and we use it all over the place in testing. It's a really easy way to do system testing for really complicated things where you're composing a number of different services or whatever together, and you have the network faked out, and you have your storage faked out, and everything is just running in one process. And it's really nice. When something is very complicated and you can get it running in a simple in-memory fashion in one address space, that's beautiful, and it makes it way easier to verify that things are correct. Abstracting over buffer and flush policies is super, super important. I'm sure many of you have written this code a whole bunch of times. If you've worked with data much, we all have. It tends to be done on a case-by-case basis in different places. It happens for messaging, right? A lot of things like, for example, the 0MQ thing. I don't know if you guys have heard of this 0MQ thing. It's like a supposedly fast queue, and they say on their webpage, it's faster than TCP. And I'm like, faster than TCP? What the hell are these guys doing? And so I went to go look. Oh, they're buffering, they're buffering message. That's not fast. It's transferred over TCP. It's called buffering stuff and sending it over TCP. There's nothing new there. But the point is, we do that all the time. It happens constantly. And sometimes it's happening for storage because it's expensive to merge something. Sometimes it's happening for passaging messages across the network. But the problem is, it's tedious kind of code to write, and you'd rather not write it for every single different purpose. So this is the kind of stuff that you want to abstract, get it right, nail it, and never do it again. And so that's the kind of stuff that the store and what we're going to show in a minute, the graph library, are all about. So onto a concrete example with the store, merging. We're going to do indexing bigrams, really simple. So first, you see we set up the store here, and it's an in-memory store. And its merge function is our good friend merge with plus, right? Pretty simple. And then we're going to do seek over the partitioned words. And the bigrams are going to store indexed on the first word, all the counts of the subsequent words. That's it. It's really simple to index bigrams with this stuff. Second example is MapReduce. We're going to do a trivial MapReduce, and then we're going to do one that's going to go through 3 or 4 different slides and talk about some of the real details. It's going to get slightly more real, not shit is getting real. And where it's not going to be distributed or anything, but it's going to deal with like aggressive pre-aggregation. So it'll get a little funkier. But in the simple example, we just have a bucket spec here with a reduce function in it. Again, that's all we have. We have a whole bunch of buckets that we're making. That's the BS here. And we have this worker function. The worker function is just taking outputs from the mapper. The mapper can generate many. That's why you see the do-seek here over the key value pairs. And we're merging, right? So again, the whole reduce thing is just being taken care of by the merge. And then over here, we create all of our workers, and we're just using our do work function that we have. The do work is dealing with all the nastiness of the underlying Java executor stuff and Java concurrency and practice stuff. We don't use a ton of the Clojure concurrency primitives, I should add. It's nothing necessarily wrong or against them. It's just that a lot of times we're doing things where we really need fine-grained control, and we need to create these pools. And we really need to maximize resources and be smart about that. So a lot of times we found that we just go straight to the executor stuff directly and control it there. And then we just reduce over the values. So this is a pretty trivial example of a MapReduce. So now getting into a slightly more realistic version. So mostly the same. We have the main aggregator bucket set up at the top. We have a worker pool that we've set up. We've got an in queue because we're going to be giving all the tasks into the workers with this in queue. We have a sentinel value to know how we're going to be done. And this is a thing, just as an aside, a lot of times people will talk about streaming or batch computing, and everybody's talking about, stream processing and blah, blah, blah now. And it's the same thing, except that you have a sentinel, right? That's how you know when you're done. I mean, that's always how it works. It's not really that big of a deal. You have the same plumbing in both cases. And you're going to see in here, right, like in 2-3 slides, you're going to see all the mysteries revealed to you of how to do like stream and batch, right? It's really not that big of a deal. So we have our setup here, and we kick off our future, and our future is going to fill the queue, and it's going to stick the sentinel value in the end there. You see that? So that's it. Now, the second part of the setup has to do with all the latching. Right, so you need one global latch for the whole job to know when you're done, and each mapper needs a latch as well. And then you have your terminator function here. Your terminator function is basically wrapping the mapper, you see that, at the bottom, checking to see if you're hitting the sentinel, and if so, you're counting down on the terminator latch. So that's basically saying, once I've seen the sentinel, I know that all work to be submitted is being processed by somebody, but I don't know if I'm done because other people can still have tasks in flight, right? So it's safe for me to count down my terminal latch there, but it's not safe for me to be done with the job. So this is just basically how to wrap each mapper and make sure that each mapper knows how to check whether or not things are done globally. And then we create these buckets again because each worker here has its own bucket. So the whole purpose of going through all these gymnastics here at the beginning is so that when the job is running, each mapper is able to aggressively merge before any kind of barrier has to happen at the end, right? So everything is all the way done so that by the time the very last computation happens, almost everything is complete, right? And there's only a tiny amount of work to be done there. So you really try to remove all the barriers that you can. So here we're going to submit all the jobs. So we're do-seeking over the buckets, and we're submitting all these tasks to the pool. You can see here, earlier we had the code for the one global latch. You can see that here we have the countdowns on the mapper latch. You can also see that we need to check the terminal latch as well, right? Because we don't need to bother checking for any more work if we know there isn't any. So I don't think I need to walk through each line by line on. Yeah, let's just skip that. And then at the very end, you have the awaiting, right? So you check if you're waiting for the terminal latch, then you're waiting for all the mapper latches, and then you're ensuring that everybody is fully merged into the master bucket, and then you're done, right? So that's it. It's really not that much code. It's not that hard to build this kind of stuff. And the whole reason I bring it up is, again, because the fact that it uses buckets, right? And there's papers about this, actually, about speeding up MapReduce and doing smarter, more efficient partial aggregations and so on. And the whole reason that this stuff is cool is because basically, instead of doing a Hadoop or one of these other things where you have no control anymore, and if you want to try to do these modifications in Hadoop, you have to go in and modify the Hadoop code base, which is kind of funky. And you have to try different things. Like, we've read some papers about people trying to do this kind of stuff with BDB, like basically partial aggregations, and then trying to speed up and reduce the bottleneck. And when you build these smaller abstractions and you build everything else in terms of those, it's just way easier to do this kind of stuff, because you have most of the tools there for it already. And most of the difficult part in dealing with this is all about the storage and the aggregation. And you can see from this code here, right, it's really not that much code to deal with a pretty complicated task that also has correct concurrency semantics in a fairly tricky scenario. And it's really like, I mean, even on slides, it's only a few pages of code, right? And in Emacs, that's like a half a screen. So it's really a small amount of code. All right, next up is going into the store library here. So we've seen some examples. I want to tell you guys what they're all about. So the two patterns that come up all the time, and we have these wrapper policies around stores that deal with, so you only saw merging there, right? There was no flushing. And one of the harder parts is actually the flushing. Like, you're building up this merge data. How often do you flush it? Where do you flush it? Et cetera. The longer I've worked with this kind of stuff, the more I've realized that all the gymnastics around the data are mostly related to the buffering and the flushing, or the caching and the checkpointing. These two kind of go together, right? Because if you're going to cache something, you don't want to flush it all the time. When you need to persist it, you want to checkpoint it. So you basically want to take a seek of everything, and you want to checkpoint it to disk, but you don't want to drain seek. You just want like a checkpoint seek, right, is what we call it. And so the opposite is true when you're flushing. If I have a bunch of writes coming in and I'm going to smartly pre-aggregate everything before I write it to disk, then I'm going to merge them all together and I'm going to flush. So the reason that I'm bringing this up is that we're relying on the seek underneath it, right? So even on the backside of the store, we're decoupling then from that protocol and just emitting seeks. And not really, so it doesn't have to be like hot store on store action, right? It can be you can have seeks going anywhere, and we're going to show that in the last example here. After we talk about the graph a little bit, I'm going to go into an example where we actually flush a seek, which is then updating some custom in-memory data structure to be used in the online system. So, all right, what is the graph thing? The graph thing is pretty simple. It's like a better API into doing like distributed computing than like a MapReduce kind of a thing. It's more or less the same idea as Microsoft's Dryad. It's pretty simple. You just have a bunch of functions. You want to compose them into a DAG, and you want to decouple the execution plan from that DAG. That's really it. And you want to optimize it for throughput. This is, again, why we don't use like Hadoop or any one of these things, because we want to express our computations in a way that can run in our production systems live with online data, getting online updates, and then serving results up to users. We want to use the same code there that we would use to run over all our historical data to do training. We don't want to split those up. And we don't want limitations of batch updates, so we don't want any of that. But at the same time, we want it to be fast. We want it to be scalable. So we kind of built up these abstractions of our own. Let's go through an example here that's really simple with the graph. Let's see. So first thing we're going to do is fetch docs. So you can see like the syntax here is pretty simple. We're going through the pipe. We've got the same functions as Clojure, but with a G in front of them. We're first fetching a bunch of docs. Then we're tagging them with entities. That's what this NLP extract entities guy is doing. And then we branch. So that branch statement there, you see the terminal IO vertices there. One is a bucket merge, and another one's publishing on PubSub, right? So this is the kind of pattern that we do all the time with graphs, is you set up a computation, and the terminal nodes are I/O, and it's basically always a store or PubSub for all intents and purposes. And so this is a pattern that came up so much that we kind of like built it in and made it really simple to do. So the inputs and outputs play nicely with that. Also, I should mention they get their inputs all the time for this. So the input scenario that comes up all the time is you start up a graph, and you have some data on disk, which is going to prime it, and then it's subsequently going to be getting all of its data from live events. So it's also a very common scenario that you start up a graph, and you have a priority queue on its head, right? And then you start up a job in the background on a future or whatever, which is going and reading data in from disk and dumping it in. And then you have that same guy up on a listener, which is getting hit with inbound data. So that's a pretty common scenario that we do as well. And that's what happens, for example, when you, if you reboot like one of our core machines that runs our news feeds, for example, that makes everybody's news feeds, they have to read in very large amount of data into memory. We're using the big instances, like the cluster compute guys on Amazon. And so they're reading in gigabytes and gigabytes of stuff into memory when the service starts up, but you don't want it to be dead, and you also want it to be available for accepting live events, right? So this is a very common system when you're dealing with streaming data. So we've taken pains to kind of try to abstract that stuff, so it's very easy to put a new service up like this. You can do it in a couple of hours. So the execution policies are also really important. For one thing, you want to be able to test this stuff. If you've written like MapReduce jobs and stuff like that much, you know that it's kind of a pain in the ass to test. People have even written weird like testing harnesses for this stuff. But the main reason it's a pain in the ass is because you can't just test them like normal functions, and there's absolutely no reason why you couldn't do that, except for the fact that the things were written as frameworks by people who didn't care much about this kind of stuff. So what you'd like to be able to do is define one of these graphs and then just compose the thing into one giant function to test. And that's what we can do with our trusty function called graphcomp, which actually does what it sounds like it does. You also can run each node, each vertex, inside of a thread pool, all on one machine. So you could have 20 different nodes, each in its own thread pool. You could schedule them all in one thread pool, or you could schedule each one on a different machine. So it's completely decoupled, and you can run it in a variety of different ways. But there's another bigger win, I think, probably from this. You can abstract the execution policy. That's cool. You can fan out execution in a variety of ways, and you can eventually. We don't do this now. It's pretty primitive, but eventually we can have a really, really, really smart planner there, right? Eventually we can know the mathematical properties of each function and know whether it's optimal too. And we can also monitor their perf in real time. And so when you know its properties and you know its execution profile over time, then you can really smartly and dynamically plan how and where you execute these vertices. And that's really cool. But the bigger thing, which is a huge issue in production systems, is the monitoring and the visibility stuff. And I would say for most of the kinds of systems I've dealt with in the past, it's pretty weak. Even at Google, I was at Google for a while, they have a really elaborate system for querying over logs and such, because almost all these systems have always been built, with this metaphor that when things go astray, it just writes out something to the log. And I think logs are a really bad idea. And I don't know why we have that. There's a whole cottage industry called log analysis, which is just created to basically query over logs. And it's like, well, why the hell are you doing that in the first place? Why are we creating a whole industry to find crap out of data that we wrote out as strings when we had all the information about it in the first place in memory when we wrote it there? It doesn't make any sense at all. And it's making our lives miserable. It makes debugging terrible. It's like you can't monitor your stuff in production. So it's just like, why do we live like this? Why do we permit ourselves this miserable existence? And I don't understand, because we don't have to, right? So that's what we do. Because you have all these nodes in the graph are just functions. Well, you just wrap them, that's all. You just use higher order functions, and then you throw up exceptions or you do whatever you want to do, and you capture the data, and then you can write it out. It's pretty straightforward. So here's what kind of like an example looks like of one of our dashboards, right? So in the graph example, I also forgot to mention, I should have mentioned this. Some of you might have been wondering what these little IDs are. So we're using keywords as IDs for each vertex, and we don't have to do that. They don't have to be there. They're optional. But we always do that in order to give them descriptive names for monitoring purposes. And obviously, you can just like introspect and look at the function name, but that kind of breaks down with lambdas, right? So because we want to be able to like do partials and lambdas and all that kind of stuff, we found that it's actually just easier to manually tag these things with IDs. It's a small amount of work given the debuggability benefits. So you can see what we're doing. We're looking at the number of times things have been executed, what their throughput looks like, what their CPU time looks like, the number of exceptions that each one has thrown, the number of each type of exception that has been thrown. And all this kind of information is really great. I mean, as soon as we got this kind of stuff up, this is the first time in my life that I've ever run anything like this in production with this level of visibility. And it's just so liberating. It really, really is. To be able to find where things are screwed up and notice where data is being lost. Like the first time we got this thing up, we literally found that we were dropping like 85% of the data on the floor. So I mean, seriously, 85% of articles that were coming in were just being dropped on the floor, from parsing errors or all kinds of other shit, right? So a lot of it is pretty trivial to fix when you can see it in a clean way. But you can't see it like, like Neo looking at the Matrix thing, like falling down in front of you in the logs, right? You can't find anything that way. It's just a disaster. So with this, it's great. You can really fix stuff. And so just practically, that's a huge win. We use graph to compute and monitor. Again, like the same abstractions are useful for anything, right? Just like with all of FP. It's like if you just deal with functions, you can always wrap them. You can inject them into other functions. You can do whatever you want to do. And so the same thing that gives you that composability for computing gives you that composability for monitoring. Again, it tends to always, at the end of a graph, have a terminal store node or pub sub. It will pub to another graph. So like concretely what happens with us is that data comes in from somewhere that we pulled or crawled. We find out, have we seen this link before, et cetera. There's a lot going on at that stage. And then it passes off to a big pool that deals with documents, and that knows how to fetch documents, how to label them, how to do all the text extraction, et cetera. Also clustering, and then it gets passed off to the services that are user-facing, which are building feeds and performing other tasks like that, right? So between every single one of those things is running a graph, and they're oftentimes both pubbing out their data to a subsequent graph and writing it out to a store. And this allows us to quickly craft systems for all kinds of problems. So if we need to do a new thing, like there was a time that we decided to index Wikipedia. We didn't know. Wikipedia is one of these things where there's been a lot of people for years like doing semantic web kind of stuff with it and whatever, and most of it's nonsense, so we didn't use it forever. We were like, this stuff's mostly rubbish. But we did decide to play with it one time, and that was an example where it's like it was literally like 4 or 5 hours to go from like I've never seen Wikipedia data in my life to like now we have a fully indexed Wikipedia, and we're looking at n-grams and stuff. So that's the whole purpose of all this stuff, right? Is that with this kind of composability, it allows you to tackle a new problem really quickly, because you don't have a bigger thing that's suited only to one particular task. You have lots of smaller stuff, and you can kind of munge it together in the right way. So now we're going to come to this example I was telling you where we have both a graph and a store. The purpose is going to be doing online learning over streaming events, but the catch is going to be that updates to the online model are very expensive. So you don't just stream data through and update the model straight away, because those updates are costly and the data is coming in very frequently. What you're going to do is batch stuff up and then update periodically, right? So we're going to trigger them after we collect enough events, say 10,000 user events or something like that. So here at the beginning, we have params. Params are kind of learned parameters for ranking. And the sufficient statistics are coming from the current iteration. We're going to update those params with the sufficient statistics every so often. So you can see here we do the gmapcat over the features. We extract them. Then we merge the sufficient statistics here. And then just on this little cron job, I think this is kind of wishful thinking on the syntax here, but we have this cron job running every 60 minutes that's updating the params. And here at the very bottom, you can see the example I was talking about where we're flushing that bucket just so you understand what's happening. And that update params function is actually taking a seek as its second argument and updating the in-memory params. And we do this kind of stuff all the time where we go back and forth. So I don't want you to think that everything is all in these holy abstractions that are just like perfect or whatever. It's not the case at all. And that's the whole point. Some of the data in, say, for example, in our social feed service is stored in these very highly customized and very, very efficient data structures that are all like custom protocols and everything, right? It's not using any of these abstractions at all. But then something else that writes data to it will be. So this kind of scenario is fairly common where you might have a bucket thing, but then something on the other side is this like super tuned, very, very focused solution to a particular problem. And this kind of stuff is like great for going back and forth, right? Because you've got these finer grained things. I don't have to depend on a particular data store or a particular way of storing data in memory, and like everything has to get munged into that paradigm. We don't do that because of exactly this kind of thing. So I think that's it. So I wanted to show you guys a demo really quick, and then you can bug me with questions here. Well, not really bug me, but you know what I mean. So let's see if I can get this thing to actually like collapse to a reasonable size. Here we go. So here's the product. Oh, I'm on staging right now. This is because we have our new landing pages here. You guys want to see the new landing page? It's pretty awesome. I'll show you this really quick before. Isn't that great? Look at that. Isn't that awesome? Hold on, look at the button here. I'm really stoked about that button. See that? See the press state here? Boom. All right. Okay. All right. Let's look at the real product now. Sorry. Okay. So this is what it is. It's pretty straightforward, kind of newsfeed type of experience. We tried to get all the rubbish out of the way for the most part and keep it pretty simple. So you have a home feed. You have favorites, shared, and read. This is just stuff that I add, right? So like this takes care of like the read it later kind of scenarios and so on. Also, like over time, this will get more sophisticated. The thing that I've always hated is that, I basically like can never find. Sharing and bookmark are kind of the same thing for me, right? So if I find something cool, I might share it out or I might bookmark it or whatever, and then I can never find all this crap in one place. So we're trying to move toward that so that you can have kind of search over your personal interaction items across the board, no matter where you share it to. So you can see, like, this is a great, I have a really good mix of topics in here, I guess, because I'm getting all, like, really nice visual stuff, right? From Nano. And you can see again here the topic diversification, right? So we got gardening in the front, then we move on to this. Oh no, I'm in my favorite feed, so it's a bad example. That's all awesome because I actually favorited it. It's a red herring. But here's the same thing, right? So you have design and interior design, which is something I'm really into. Then San Francisco is next, where I'm from. Again, more interior design stuff. Here's something about China, which is an area I'm interested in. So it's like it's doing a good job of kind of, flipping between different stuff. Here's something about sustainable energy, right? So it's taking my different interests and it's diversifying so that I'm getting a lot of the kinds of top stuff that I'm into, but it forces me to not consume only that, right? So that's pretty cool. Also, the navigation model that's interesting here is like, so, okay, sustainable design, right? I want to go there, boom, I'm there. So you see how fast that was? That was all dynamic right there. That happened at request time, right? So this whole feed here was built and re-ranked for me dynamically when I issued that request. So it's hard to stress how hard that is. It might not seem like a very big deal. That's really hard to do. So I just want to make sure we're clear that that was awesome. So that's really it. And then there's search. I'll do this one thing and then I'll be done. So search, it's giving me some suggestions already, right? But if I do, like, let's try GOP. Gophers football, that's pretty weird. I don't know what that's doing. But the other things are what you would expect, right? So the query expansion is a long topic similarity. So you're going to get whatever in real time right now is kind of most similar to the query that I issued. So I can get results for the election and come into that feed, and I can see what's going on in the election. And so what we're trying to do here is encourage people to have that home feed experience where you sit there and everything comes to you, which we've gotten used to from like the Twitter and Facebook kind of world. But the problem that we're trying to go after is say, well, that's great and the simplicity of it is beautiful, but if you're stuck only there, you're only going to see the stuff from your friends and you're going to keep getting caught in this bubble. You're going to be in the echo chamber for the rest of our lives. And so what we're trying to do here is give these easy windows to explore out, right? And then now I can come and explore campaign finance. I'm sure that's something I want to spend my time reading about. So that's it. Thank you very much.